So this case study is from the topic of semiconductors. Let's read the case study first and then try and attempt the questions. So this is from the previous year questions of CBSE. Let's read it. Okay, so a semiconductor diode is basically a PN junction with metallic contacts provided at the ends for the application of an external voltage. It is a two-terminal device, okay? When an external voltage is applied across a semiconductor diode, such a P side is connected to positive terminal of the battery and N side to the negative terminal, it is said to be forward bias. Okay, yeah, this is one mode of operation. When an external voltage is applied across diode that N side is positive and P side is negative, it is reverse bias, right? So we already know what is reverse bias and forward biased. An ideal diode in which resistance is forward biasing is zero. Yes, there is no resistance when you're in forward bias, and the resistance is infinite in reverse biasing. Absolutely, it does not allow any current to go through it except a small current, which is a leakage current. When the diode is forward biased, it is found that beyond the forward voltage called as a knee voltage, the conductivity is very high. Absolutely, there is a sudden increase in the current, even though the amount of voltage you have increased is very small. When the biasing voltage is more than the knee voltage, the potential barrier is overcome and the current increases rapidly with increase in forward voltage. Exactly. So, okay, when the diode is reverse biased, the reverse bias voltage produces a very small current, about a few microamperes, with almost remain constant with So this is the IV characteristic of the diode being described in the reverse bias. This small current is the reverse saturation current. You know, it is represented at IS. So IV characteristics of diodes are very, very important to understand. If you can go and watch my live class on semiconductors to watch IV characteristics. Okay, so we have read the forward bias and reverse bias of a diode and what happens in the two modes of operation. Let's attempt the questions now. In a given figure, a diode is connected to an external resistance of 100 ohms, yes, and an EMF of 3.5 volt. If the barrier potential developed across the diode is 0.5 volt, the current in the circuit will be how much? Okay, so the potential here, which is a barrier, is 0.5 volt, right? And what you're applying externally is this. You can see the positive terminal is connected to the P side, so the diode is forward biased, right? So 3.5 volt will get applied, but it will face 0.5 volt as the barrier potential. So the battery will beat the barrier potential, and the net potential which will be left in the circuit will be 3 volt. And what is the resistance in the circuit? This. So what is the current in the circuit? V is equal to IR. So 3 divided by 100 is equal to 0.03, or we can say 30 milliampere, right? So essentially, the barrier potential is opposite of 3.5. It is like saying that you have this potential, which is battery potential, which is external, right? Which is used to bias the diode. But the barrier potential acts in an opposite manner when you compare it, okay? Let's move to the next question. In which of the following figures the PN junction diode is reverse biased? Okay, so for reverse bias we know, for reverse bias we know that the P side has to be connected to the negative terminal, which means the P has to be made at lower potential and the N side has to be kept at the higher potential. So it's reverse. So let's look into the diagram where the triangle, which is a P side, is connected to the lower potential. So here 0.5 volt is bigger than -12. This is essentially forward bias. Now the P side is connected to 0 and the N side is connected to -10. So -10 is connected to lower potential. P is connected to higher potential. This is also forward biased. Let's go to this. In this, the P side is connected to 0 volt. This is a sign of grounding. It represents 0 volt. And the N side is connected to plus 5 volt. Okay. So in this particular situation, what we have is reverse bias, because the P side is at lower potential and this side is at higher potential. And let's evaluate this. The positive side is connected to 10 and the negative side is connected to 5. So this is also forward bias. So this is the only one which is reverse biased. Okay. Based on the VI characteristic, we can classify diode as, okay, first of all, the straight answer is it is not a ohmic device. So if you go back to your graphs of VI characteristic, which I'm telling you is very, very important, it is not a ohmic device because it does not follow the rule of V is equal to IR. It does not, right? So we can't really apply it. Now let's go to the next, bilateral device. What is a bilateral device? A resistance is a bilateral device because it allows the current to flow in both the directions, but diode only allows the current to flow in the forward bias. So diode is not a bilateral device. Even this is wrong. Okay, it's not a passive element. Okay, it is definitely an active element. The only logical choice is your non-ohmic device. Okay, so it does not follow Ohm's law. Straight answer. So the choice given with third is this. Let's look into this choice also. Let's read this question. Appears to be very interesting. So you have two identical PN junctions which can be connected in series by three different methods. If the potential difference in the junction is same, then the correct connections will be, okay. So you can see two diodes being connected to each other in three different manner, and you have to decide which combination or connection is right if the potential difference across the junction is same. Let's look into this. PN. So this is forward biased. There will be actually the barrier potential will vanish after certain voltage, 0 volt. Okay, this is reverse biased, right? So this is reverse biased. So the potential will be very high. So this cannot be included, right? Because here this is forward bias 0 volt. Here you will have larger barrier potential. So the potential has to be same, right? In the question, we have to select the choice where the barrier potential is same. Here the barrier potential is not same in this case. So this is wrong. Let's look into this. This is forward bias, forward bias. So both will have same barrier potential. In fact, it will become 0 if the barrier potential is overcome beyond the knee point of the VI characteristic. So here the potential remains the same. Both are forward biased. Let's look into this. This situation, you have both of them to be reverse biased, right? So even here, the biasing is same and therefore the barrier potential is going to be same, right? Which is the potential difference in the junction. So the correct choice here is your 2 and 3. Tricky question and a good question to attempt. Let's go to the next part. All right, so this question, the last part actually has come from the NCERT book. It's a solved question. Okay, what is, see, this is a IV characteristic. You anyway can get a question that says explain the IV characteristic of a PN junction diode. So there you have to explain all types of voltages, the saturation current, right, which is this one, and you know why this voltage is rising rapidly, stuff like that. So you have to explain anyway, right? And this is I versus V. So this first quadrant is all forward biased and the third quadrant is all reverse biased, where you hardly see any current. All right, it says that the VI characteristic of the diode is shown in the figure. The ratio of the resistance of the diode at 15 milliampere to the resistance at is given by what? Okay, we have to find the ratio of two resistances, right? So first of all, let's go to 15 milliampere. Basically, is a solved question in NCERT. Partially, the second part is not available. How do you find the resistance of a diode? See, resistance of a diode continuously varies because it is not a straight line, right? In Ohm's law, you're able to use a straight line and say V by I represents the R. So tan theta is equal to R is equal to V by I. This is your simple situation in the case of Ohm's laws for metals and conductors. But in semiconductors, you cannot do that. then how do you find the resistance of a semiconductor in this situation? Okay, so let's say you have to find the this diode's resistance, which continuously varies. You can see it's not a straight line anywhere, right? So the way to find the resistance of the diode is basically dV by di, which is the slope of the line at that point where you're finding the resistance. So you're finding instantaneous value of the resistance. So he's saying calculate the value of the resistance at 15, right? So if you notice this graph, right, I will say that 15 milliampere practically appears in the middle of 0.7 and 0.8, right? I also need to find out what is the value of the, so you're saying you are finding the slope of this graph, which is the dV by di here, right? We are drawing a tangent here. You have to find it, right? So if you notice, this 15 milliampere is in middle of 0.7 and 0.8 also, right? So can I write it as, so the voltage is approximately, let's say 0.75 volt, right? And the current is 15 into 10 raised to power minus 3, right? So this actually becomes what, 75 into 10 raised to power 3 divided by 15. 15 fives are, and this is minus 2. This becomes approximately 50 ohms, right? So the resistance here is 50 ohms. NCERT has done it in a different manner. Don't worry, even this method is right, because we are calculating the instantaneous value of the resistance. And in the end, I will tell you another trick which is very, very important. Okay, now let's look into this. The instantaneous value is again dV by di, which is the resistance at minus 10 volt, right? We have to find here. So this is minus 10 divided by 1 into 10 raised to power minus 6. This is a slope, right? So this is, you don't have to write this, 10 raised to power 7. You have to find the ratio. The ratio is going to be, therefore, so the ratio is going to be 50 ohms divided by 10 raised to power 7 ohms. So approximately, if we calculate this, right, this actually comes out to be 10 raised to power minus 6 as a ratio. This gets cancelled. This is 0.5 into 10. Order is of the 1 million ohms. So which is the correct answer here? The correct answer is the, let me just rub this off so that you can see the correct answer. I think the correct answer is 10 raised to power minus 6. Okay, that is your answer. Now I told you I will tell you another trick here. Okay, supposing you're given that the IV characteristic of a the diode is given to be I is equal to 2V square, example. So what you have to do is, and you have to find the resistance of this diode when there is a value of voltage is given or current is given. So what you do is V square is equal to 2 I by 2, and V is equal to under root of I by 2. You have to calculate the value of dV by di, right? So this will be half under root I, and so there is another root 2 here. So this becomes 1 by 2 root 2 under root I, right? If you're given the value of I, where you need to find the resistance, say I is given to be 25 milliampere, right? So you will write it as 1 by 2 root 2 5, because the square root of 25 is 5. So this is your answer, resistance. So this is in milliampere. This will become 10 raised to power minus 3. This will become 200 by 2 root 2, and this will become 50 root 2 ohms. So sometimes the diode questions can also come like this, where you need to use the derivative. The derivative of the equation will give you the value of the resistance, dV by di. So I hope you found this video to be very useful. You have to do some case studies from each of the chapters, because it's very, very important that you not only learn the standard theory, but also you learn how to apply it. So this particular question had good amount of analysis and also good amount of graph which was used, right, to solve the problem. So thank you very much for your time, and let's wait for the next video now. Thank you very much.